Hello, everybody. Welcome to our fifth webinar in this monthly webinar series, Lunch with the NMSP, Food for Thought. Today's webinar will be all about the value and the power of manure. Before we dive into the webinar itself, I wanted to introduce our program to you real briefly. My name is Corinne Ketterings. I lead the Nutrient Management Spear program here at Cornell University. We are an applied research and extension program. Motto is relevant questions and sound science for agriculture profitability and protection of the environment. All our work focuses on development of tools for implementation at the farm level with crop advisors, nutrient management planners, and we link up with the policy folks in the state as well. Our team has 6 focal areas. The first one is the land grant responsibility to develop and support the implementation of land grant university guidelines for nutrient management for field crops. We work in soil health and climate resiliency, precision agriculture, dairy sustainability. We lead the on-farm research partnership in the state of New York, and our 6th pillar is to focus on student engagement. Last August, we celebrated our 25th year in existence at Cornell University. And with that, we also launched our webinar series. So far, we have delivered 4 of those webinars. Today is the 5th one. The past webinars are posted on our YouTube channel. And today's webinar is about the value of manure. Next month's webinar, also the first Friday of the month, is on pH and lime management. So May 1st, pH and lime management. There's a link here to sign up and register for that webinar series as well. I also have on the screen here on the right our access to social media, including our website, our LinkedIn channel, Facebook, Instagram, X, and the YouTube channel. So if you're interested in checking things out, the new newsletter just came out this morning. With that, we're going to dive into our webinar for today. I'll be co-presenting here with Juan Carlos Ramos Sanchez, our on-farm research coordinator in the team. We also want to recognize upfront the contributions of many of our team members here, as well as participating farmers, extension educators, crop consultants, agency staff. The information that we're going to share here today very much reflects a partnership within the state of New York, and hence the listing of some key people. So with that, we're going to dive into the outline. There is a chat available for the webinar today. If you have any questions as we go along, please feel free to enter those in the chat. And Carlos and I will try to monitor that as we go along. For outline, we start with a little bit of information backup on dairy farming in New York and the crops we grow and the crop needs in terms of growth and production. Manure variability, crediting manure nutrients. Very briefly talk about injection of manure in the fall. And then Juan Carlos will also spend quite a bit of time talking about our statewide value of manure project that we've been working on for the past 4 years. A little bit of information on some laboratory evaluations we're conducting now and ongoing projects moving forward as well before we wrap up. So for those of you out of state, maybe less familiar with New York agriculture, dairy farming is really important for the state of New York. Currently ranked 5th in terms of milk production. And that also means that a lot of our land base is dedicated to growing the crops that benefit our dairy farms, forages and cash grain as crops as well. Large number of acres in hay crops, corn silage, corn grain, and also soybeans. If we take a look at these crops, and we want to grow the best available crops with the best quality for our animal agriculture, we got to realize what these crops actually need to grow and produce. And that does include things like oxygen and water and light, structural support, something to anchor the roots into,
some nice temperatures, but it also includes things like carbon, proper pH, and nutrients. The focus today will be on nutrients to start out with, but we hope to share some other information here today too to show you that that's not the only thing that counts. When we take a look at all these nutrients, there are 17 essential nutrients. They're all essential for crop growth. If a single one of those is missing, a plant cannot fully grow and produce. We divide those nutrients into three groups. Primary macronutrients, nitrogen, phosphorus, potassium. The secondary macronutrients, calcium, magnesium, and sulfur. And then we have the micronutrients. They're listed on the screen here. The only difference between the macro and the micronutrients is that the micronutrients are needed in smaller quantities than the macronutrients. They're all essential. They're just taken up in smaller quantities than nitrogen, phosphorus, potassium, and the other secondary macronutrients. When we take a look at the state of New York, and particularly here in the slides, we're showing the state phosphorus and nitrogen balances. This is for 2017. We are close to wrapping up also the assessment for 2022. So that will become available later this year. If we look at these balances, there's nitrogen and phosphorus here. I want to zoom in on the phosphorus side, so the left side of the picture here. If we take a look at this, we see on the left the crop uptake of phosphorus. In dark green is phosphorus represented in the crops that are not legumes. So corn silage, corn grain, crops like that. Hashed area is the amount of phosphorus also taken up by the legume crops that are grown in our state. So we get a total amount of phosphorus represented in the crop yield of that particular year listed here. And we compare that on the right side to the amount of phosphorus that we supplied through fertilizer, the red portion, and through manure that is generated on the farms in New York, the brown portion here. There's two things we want to point out in this slide. The balance, well, three things actually. The balance is 9 pounds per acre, which is really good. An advanced view here, the 2022 balance is even lower than that. The things we wanted to point out here, when we compare what is taken up by the crops to what is supplied to grow those crops, we see that if we would not have manure in the state of New York, it would immediately mean we would have a much higher need of fertilizer phosphorus. So this illustrates that manure offsets quite a bit of fertilizer use in the state of New York. If we did not have manure, we would need more fertilizer, phosphorus in this case. The second thing I want to point out in here is that if you look at the brown box here, you see that is smaller than the combination of legume and non-legume crop phosphorus content. Manure alone is not enough to balance for crop removal for phosphorus in the state of New York. And that difference is actually bigger in 2022. So there is a place for fertilizer within the state of New York. There's one more argument we want to make with this figure, and that is if we did not have manure, we would fully expect the crop yields to go down as well. And we'll come back to that at the end of this webinar. And that I'm going to hand it over, and Juan Carlos is going to talk about manure variability.
Thank you, Corinne, and hi everyone. So we are learning that manure is a great fertilizer. It can reduce our reliance on synthetic fertilizer as well, increase sustainability. But then it also comes with some challenges, especially from the side that the composition, the nutrient composition in manure can be quite variable. So it can be difficult to manage the variability and now how much nutrients you're actually applying to a field. So with that in mind, we had a study, manure variability study, where we were collecting manure from spreading equipment in several farms in the state. And this is a good reminder about the principles of right manure sampling, and these are the ones that we follow for that study. Number one is that we should sample from the application equipment, either from the spreader or from pumping equipment moving that manure. So we have the composition of the manure that is actually reaching our fields. Second, fill a 5-gallon bucket. And third, from that 5-gallon bucket, grab 3 subsamples. And this is important because if we ship those 3 subsamples to the lab, we are able to identify outliers. If something happened during the collection of the sample or in the lab, we are able to identify the outlier, take it out, and have the numbers that actually represent the manure that we are working with. So for this study, we work with 4 dairy farms in New York State. We were collecting samples every day, and during that daily sampling period, the farms applied a total of 27.5 million gallons of manure. And we were also, for fewer days, intense sampling, so we would spend the whole day in the farm and sample manure every 2 hours. And we were able to cover 5 million gallons applied during that intense sampling protocol. Now moving into the results, here all of them are coming from the same farm. The difference is that this farm had 4 different storage units. So we focus on the first 4 columns, that's total nitrogen, and then we have that composition in pounds per 1,000 gallons. We see that there's quite a bit of variability between the storage units, especially storage 2 and 3 are way higher than 1 and 3. And we see that that trend is also in P2O5 in the 4 columns in the middle. And then the same is going on for K2O, the 4 columns on the right. Storage number 2 and storage number 4 have a higher nutrient composition. And this is telling us that we should sample each storage unit individually. The different management or different manure type that is going to each of the storages is going to impact the composition. And we should also track where that manure is going to, which fields, manure from which lagoon is going to which field, so we know the actual composition of the manure applied to each of our fields. So our second learning lesson here is in this farm, they were doing agitation, and those are the 4 columns on the left. That's pounds per 1,000 gallons of total N, P, K, and dry matter. And then on the right, we have the same farm, the same application event, but then when they stopped doing the agitation. And what we can see here is that the agitation actually lowered the composition of total N, P2O5, and dry matter, especially dry matter, went down from 4.5% to almost 1%. So we can see how as the dry matter was going down, also total N and P2O5 concentration was going down in the manure, while K2O stayed fairly constant. So no agitation means probably a lower nitrogen and P concentration because those nutrients are settling, and changes in dry matter are likely connected to changes in nitrogen and phosphorus. Then for this slide, we are looking at the coefficient of variation in our y-axis. The higher the coefficient of variation, it means that there's more variability between the samples that we collected. And we have columns on a solid color. That's the one that those are coming from our daily sampling. So we see the variability between days. And the ones that are dotted or dashed are samples coming from one day when we did the hourly intense sampling. So if we focus on total nitrogen, we see that the variability was quite high, between 5 and 15% for these 3 farms. But the variability was higher in the daily sampling and not much variability in our hourly sampling. Something similar for P2O5, the variability was quite higher, especially in farm B, when we were comparing samples taken on different days versus the hourly sampling where there wasn't much variability. In the case of K2O, the variability stayed low for both the scenarios, daily sampling and hourly sampling. As we see the lower variability, we can conclude from this that there are important day-to-day variance between the samples. Not much going on within one day, but day-to-day it's important to be able to tap into this variability because manure composition is gonna change during your application event day by day. So we have a brief summary of those results with this nutrient behavior matrix. The location in the storage, we see that total nitrogen and phosphorus are tied to the solid fraction or dry matter. They are gonna settle at the bottom of the storage. Potassium is more dissolved, it's gonna be in the liquid fraction, so it's gonna have a better distribution across the storage unit. For the variability, total N and phosphorus have high variability, and that's connected to dry matter, while potassium have low variability, minimal fluctuation compared to N and P. Response to agitation for total N and P, it's critical. A good agitation is gonna suspend N, P, and dry matter, and it's gonna improve the composition of the manure. It's gonna be more homogeneous, and it's gonna have a higher concentration. While potassium is not that impacted by the agitation because it stays homogeneous regardless of agitation. So moving into the conclusions, we are learning here 5 lessons. The number one is that it's important to isolate the asset, sample every storage unit independently because they're gonna be different. Track the flow, maintain unit-specific storage to fill application records so you know which manure is going to which field and you have a better idea of the composition. Agitate when possible because that agitation is going to suspend N and P and is going to give you a more rich manure and with lower variability. And then number 4, sample at the source. Collect the sample from the pumping or spraying equipment so you know what's the composition of the manure reaching the field. Monitor dry matter. As we show, dry matter is very well connected with total nitrogen and P. So pull new samples if you visually see differences on the dry matter of the manure.
So Juan Carlos talked about sampling and getting the right representative sample out of storages. Once we have a good sample and we can trust the numbers, or the actual sample representation, the next thing that we want to know is what are we getting out of that sample? What's in it and how do we credit it? Laboratories that do manure analysis will, at a minimum, give you information about dry matter or solids content, inorganic nitrogen, organic nitrogen, phosphorus, and potassium. That for all the labs we work with is sort of the minimum data set. This is an example here of one of the labs we work with. They will give reports typically on a dry matter basis, wet as dry as received. And then what we are looking for in these analyses is the number of pounds of nutrients per 1,000 gallons. So for liquid manure, we take a look at this column, pounds of per 1,000 gallons, and we take a look at how much ammonium N is there, how much organic nitrogen is there, how much phosphorus fertilizer equivalent is there, so P2O5 column, and how much potassium is there. Labs will analyze more than just NPK. But if you want to get the extra analysis, it's obviously at an extra cost as well. But all these nutrients that are important for us in agriculture can be measured. This is a liquid manure example. Here's an example of a more compost type product. Send in, and there we get results back with pounds per ton unit. We're going to be using this analysis on the left with the liquid manure to calculate a few things in the webinar here today. All right, crediting nitrogen in manure in New York, as well as phosphorus and potassium. There's a fact sheet as part of our fact sheet series. If you scan the QR codes, you will get to that. The very first component here we want to present to you and walk through is I have my manure analysis, send it to the lab. I got the numbers in the pounds per 1,000 gallons. This was that example that I showed you before. It's at 8.4 pounds per 1,000 gallons of organic N, 12.6 of inorganic N. The phosphate equivalent was almost 11 pounds per 1,000 gallons, and the potash equivalent was almost 13 pounds per 1,000 gallons. If I know that, I can do a quick calculation and say, roughly what do I pay for a pound of nitrogen, phosphorus, and potassium if I had to buy fertilizer? And we assume some values here. What does that then mean in total? So we take our 8 pounds of organic N, we multiply it times 62 cents as an example of 62 cents per pound of nitrogen. That gives my manure a value of $5 of organic N. We can do that for inorganic phosphate potash and add that together. This particular example, the total value per 1,000 gallons is about $25. So if I would go on my field and apply 12,000 gallons, I am dealing with a total value of a little over $300 in manure per acre. Now we should recognize that this is total nutrients. This is not necessarily what a plant would have access to. And for nitrogen, that's a really important distinction. In nitrogen, we have two different types of nitrogen, inorganic nitrogen and organic nitrogen. The manure analysis should list both independently. Organic nitrogen acts like a slow release fertilizer. Our current recommendation system says we get credits for 3 years in a row. The first year of application, 35% if it's more liquid manure, 25% if it's more solid manure. Compost type materials, we would assign 25% to, whereas the regular raw manure, we would look at 35%. Then a year later, we could expect another 12% of that organic nitrogen, and then the third year, another 5%. So 3 years slow release fertilizer contributing that nitrogen. The inorganic nitrogen side, it reacts like fertilizer would, like urea would. If we can capture it in season, it would be equally equivalent as urea fertilizer would be. If we apply it in the fall, we cannot carry that over into the next season. We will lose it before the next crop is able to take it up. So there's a zero. More common situations would be the spring season application. If we can inject or incorporate within 1 day, 65% of that inorganic N is expected to be available and captured. And the longer we wait for incorporation, the lower that number becomes. Basically, after 5 days, we don't credit anything anymore in terms of inorganic nitrogen. This is the system I inherited when I started working at Cornell, now 25 years ago, crediting system for manure in New York. The inorganic crediting is more spelled out in this table here in terms of injection into a growing crop, 100% equivalent, no incorporation or injection, 0, and then the numbers in between in terms of estimated capture of that inorganic nitrogen, depending on how it was applied and when it was applied. So if I apply that to the example we walked through, our original example was the total value was $25. But if I say, okay, I'm going to capture 35% of the organic nitrogen, and I'm going to incorporate within 1 day or inject, and I captured 65% of the inorganic N, now the value of my manure is a little shy of $20 per 1,000 gallons. So this is simply discounting some of the losses of the nitrogen that we cannot capture. 12,000 gallon spreader would have a value of $230 something per 1,000 gallon. All right.
So with that creating system, using that, we developed a phone app, the Value Manure Calculator app, and we're gonna present a video when you can take a quick look on how the app works and what are some of the numbers you can get out of the app.
Welcome to the Value Manure Calculator by the Nutrient Management Spear program. I'm gonna run through an exercise using liquid dairy manure. So to start, we need to select the animal species. In this case, it's gonna be cows, and the manure analysis units. Because this is a liquid source, we're gonna be doing pounds per 1,000 gallons. So from the manure analysis, there's a 6.4% dry matter in this manure. In the ammonium N, it's 12.6 pounds per 1,000 gallons. Organic N, 8.4. P2O5, 10.6. And K2O, 12.9. So with that, we move to the next tab, which is the current application tab. We're gonna select our rate and manure application method. So again, because we are doing a liquid source, we select a rate in gallons per acre, and we're gonna do a rate of 12,000 gallons. For the timing, in this case, I'm gonna select that manure was injected, and based on that rate and our manure analysis, I get the credits here. So for ammonium nitrogen, 98 pounds per acre, organic N 35, for a sum of 134 pounds of total N available, and for P2O5 127 pounds, K2O 155 pounds. So this calculator also allows us to calculate the value of these nutrients, and for that we're gonna move into the fifth tab, the fertilizer one. Here we need to add what's the cost of a pound of each of the nutrients. So for nitrogen we're gonna do $0.62. For P2O5 I'm gonna do 68 cents, and for K2O 0.4 or 40 cents. Because I don't have a past application yet in the calculation, there's no money coming from that, but then this is calculating the current application fertilizer value, which for ammonia is $61, organic N 22, total N, that the sum of ammonia and inorganic is, it goes up to 83, P2O5 $86, K2O 62, for a total fertilizer value of $231. But what would happen if rather than injecting we were just top dressing it? So we go back to the application method tab, the second one, and we select, in this case we are gonna do no incorporation or injection. With that, we go back to the fertilizer value, and we see that it went down to 170. So we see a difference of almost $50 because of the nitrogen that we are losing since there's no incorporation.
Perfect. So with that, we went to some of the functions in the Manure app. There are some others that you can calculate. So for that, Carlos Irias developed a user guide for this app, and some of the extra things that you can do are calculated nitrogen credits from past applications, entering crop needs to have balances, then calculated break-even hauling distances and costs, and some information to better understand the results from the app. So here we have a QR code for this guide in case you want to learn a little bit better of the tools that we have there.
So in our crediting system, we are giving 0 credit to a full manure application in terms of the inorganic nitrogen. I wanted to recognize that there are really good benefits, though. to injecting manure also in the fall, not just in the spring, to capture most of the nitrogen. Those benefits include that anytime you bring manure into the ground instead of leaving it on the surface, you will reduce the risk of phosphorus loss and you will reduce nitrogen volatilization. As we try to build cropping systems that keep the ground covered year round, putting in cover crops right after corn silage comes off, for example, or small grain harvest, it should also be recognized that that later application can also benefit that double crop or that cover crop in terms of growth. Specifically important if you grow winter cereals, for example, as a double crop to be harvested in April, May of the year. Injecting manure will also reduce N2O emissions. We'll cover that in a webinar later in the series this year. And there's an important component here also of keeping the microbes active. Manure really helps keeping microbes active and happy, and that translates into benefits for cropping systems. With this, we want to dive into our statewide value of manure project. I want to set that up a little bit before Juan Carlos talks about what we found so far by saying that back in 2015, actually, a local farmer, Doug Young, approached me and said, I would like to evaluate the benefits of applying manure. In his case, he had a piece of equipment he was building or to build to side dress manure into standing corn. And we implemented this design on his farm. We see 3 strips here that have the arrows that received the manure application. This particular example was side dressing of manure. These strips received manure application. The other strips in between did not receive any manure that year. And then we also side dressed those strips. So we subdivided these long strips into 6 different subplots with nitrogen side dress fertilizer rates ranging from no nitrogen to 175 pounds per acre side dress fertilizer. So 3 manure strips, 3 without manure. All of these strips had a subdivision into these 6 different N rates. The aerial picture speaks for itself. Doug likes to point out to the difference here between the 0 and the 175 right next to each other. The 0, but with manure, and the 175 without manure. And visually, it looks like the 0 with the manure is better. The manure strips are definitely darker than the strips that didn't have manure. We did the measurements, of course, and we're looking at 2 curves here. So here at the bottom, we have our side dress nitrogen rate. This is the fertilizer application. And we have 2 lines. The gray line here is a curve. That is for the plots that did not get manure. And then the brown is for the plots that did get manure. And there's 2 things we saw here. First was that when manure was applied, it did not need any side dress nitrogen anymore. Adding more nitrogen over the top of the manure application did not increase the yield. So the manure took care of the nitrogen needs in this scenario. But the other thing we saw here is that the difference here between the yield level with manure versus what we could achieve without manure. That is a yield boost caused by manure that could not be achieved with our side dress application rates only. Now, this was 2016. Those of you working in New York at that time might still recognize that as a tremendous drought year. We repeated it in 2017, 2 different varieties, exact same results. In 2017 was a wet year. Wet in the sense there was no lack of moisture. So this was not a moisture impact of the application of the manure. This was something else going on. Manure was boosting yield. It was not a result of fertility additions. It was not a result of moisture additions. Something else was going on. And this triggered our new project at that time, trying to expand beyond what we were doing with Doug Young at the farm those years, to a statewide project. The ability to do that was facilitated by our on-farm research partnership program. This is our on-farm research partnership that is being led by Juan Carlos. where we bring together people around relevant questions to conduct sound science for profitability and protection of the environment. A lot of people joined us for that, with also a sizable list of funding agencies that tapped into this that we will recognize at the end of the webinar.
So for these trials, we are following pretty much the same trial design as the one that Corinne explained for the 2016 and 17 plots. So first we have two layers of treatments. The one on the left is the manure versus no manure one. So for this specific one, we had strips that were 1,200 feet long and 120 feet wide. The ones on blue received manure in the spring. The ones on yellow did not. So then in the middle, we have a satellite picture of that application. You can see where the farm skipped the manure application. Those are our no manure strips. Then at side dressing time, we have the second layer of treatments applied, and that's fertilizer N in the form of urea or UAN. And each of those manure strips or no manure strips is subdivided into 6 subplots, receiving a different rate of nitrogen, going usually between 0 and 200 pounds. So for the case of this farm, it was between 0 and 175 pounds in 35 pounds increments. During the past 4 seasons, we've been able to conduct 24 on-farm research trials throughout the state, covering several important agricultural regions in the state, and I see several familiar names on this webinar, so thanks to everybody that has helped us conduct these trials. It's been a lot of work, but collaboration has been key. So moving into the results, here we have also the same nitrogen response curve that Corinne was showing before, but these are 3 new trials from the new Value Manure project. And this is what I call a scenario number 1. You see that rather than having curves, now we have straight lines. Again, we have yield on the y-axis and nitrogen rate on the x-axis in the form of either urea, UAN, so an inorganic source, and on gray no manure, on brown manure. We are highlighting in these boxes the most economical rate of nitrogen, so that's the rate that will give you the highest economic return. And then, so that's 0 in this case, 0 pounds of nitrogen. And the second number is the yield that you're going to achieve at that MERN rate. So with 0 pounds, you're going to get a yield of 28.8 tons. In the no manure scenario, for the manure one, 0 pounds for a yield of 28.5. So what we see in these 3 trials is that as we were increasing nitrogen rate, there was no increase in yield. And also there was no yield difference between manure and no manure. So that's telling us that there was no benefit from the extra side dress and also no response to the application of manure. Something important to highlight here is that these are very high yielding sites that had longer manure histories. So probably those sites already had enough nitrogen supply from the soil itself, so it didn't need and didn't benefit from the extra manure and extra side dress that we applied. Scenario number 2 is similar to the one that similar to the previous ones that Corinne was talking about, but here we see that in most cases, so I'm going to focus on the one on the top left, the most economical rate of nitrogen was 0 pounds with manure for a yield of 25.8 tons versus in the no manure ones, we needed 63 pounds of nitrogen for a yield of 25.5 tons. So when we compare those 2 numbers, we see that manure was able to replace 63 pounds of inorganic fertilizer because we didn't need any fertilizer in the manure plots to get a yield that was a little bit higher, in this case 0.3 tons higher. I won't go in detail to all of the trials, but we are seeing that in different levels, because we are testing different manures at different rates and application methods, manure is consistently offsetting fertilizer needs, and also increasing yields to levels that are not achievable with inorganic fertilizer only. Another scenario that we saw is this one where there's a yield increase due to the application of manure, but there was actually no benefit from the application of inorganic nitrogen. So in this case, we can see that there are benefits in manure that go beyond nitrogen. Some of the microbial side, soil health side that are also helping achieve higher yields. Here we have yet another scenario where we see quite a difference between the yields that we are achieving with manure versus the ones without no manure. So on the graph on the left, we see that we needed 113 pounds of inorganic fertilizer to achieve a yield of 17.1 ton in the manure strips, versus in the no manure, we actually needed less fertilizers, only 56 pounds, for a yield that was quite lower, 12.5 tons. So that extra yield that we are seeing in manure came also with an extra nitrogen sidedress need. Something similar on the trial on the left, we had a yield of 103, we had a nitrogen need of 103 pounds of fertilizer for a yield of 176 bushel in the manure strips, versus in the no-manure ones, we actually needed lower fertilizer, only 90 pounds, for a lower yield of 155 bushel. So our hypothesis here is that both of these trials were on the medium category for potassium. So manure was likely providing that K that the field needed, and that unlocked yields to new levels, and that extra yield potential came with a higher need of nitrogen. So manure not providing just nitrogen, also potassium. We were able to have research in the same fields on the following year. So the previous one were 2023, now is 2024. Same year, same fields. The only difference is that manure was not applied on 2024. We were testing the carryover benefits of the manure applied on 2023. But we did apply the different nitrogen sidedress rates. And the second difference is that because we had the hypothesis that potassium was deficient here for both sides in the spring of 2024, the farms applied a blanket potash application just to get rid of any deficiencies. So with that, we see the results that are back to the ones we've seen before, where the nitrogen need in the manure plot is actually similar or lower than the no-manure ones. So in the case of the graph on the left, 128 pounds for a yield of 23.5, versus in the no-manure ones, 132 for a lower yield of 20.9. So something important here, manure was applied on 2023. We still see the yield increase benefits on 2024, carryover benefits of manure. And then on the trial on the right, similar thing, the crop needed less nitrogen in the manure plots and had a higher yield, so 201 bushel versus 187. Blanket rate of K was added. We still saw yield bombs and nitrogen benefits 2 years after the manure application. This is one of the trials that I just presented, but we actually were able to have research also on 2025. So we have 3 years of research when manure was only applied on 2023, and we can see the benefits on year 1, 2, and 3. Not going into detail into the graph, but on the top we have a summary of the total yield for the 3 years. So with manure, we had 64 tons. And we had a need of inorganic nitrogen, fertilizer nitrogen of 312 pounds over the 3 seasons. In the no-manure ones, we had a total yield of 55.1 tons and a need of 272 pounds. So in the no-manure, it was lower because of that potassium scenario that we discussed before. And at the MERN, we saw that that manure application on year 1 resulted in a total of 8.9 tons of extra yield over the 3 seasons. And that also came with an extra nitrogen sidedress need for that potassium that we saw in year 1, but still the almost 9 tons are quite a bit an extra yield. We had something similar, so the yield benefit extended over 3 seasons. We were able to do something similar in a different farm. We had the same manure was applied on 2023, and then we tested the carryover benefits of that manure on 2024 and 2025. So in those 2 years, manure was not applied. We only did the nitrogen rates. So over the 3 seasons, here, when we look at the graph, we see that the yields were higher for manure on year 1, higher for manure on year 2, and then very similar on year 3. We saw the benefits on year 1 and 2, year 3, no manure benefits. Something different in this trial is that we were testing liquid dairy manure that was digested. It went through an anaerobic digestion process. So it has more inorganic nitrogen, more of that a quick fertilizer that is going to be there for the crop right away, but then doesn't have that slow release value compared to the previous farm A, where they applied compost, so more of organic nitrogen, slow release. So in this case, over the 3 seasons, we had a total yield of 58.5 tons with a nitrogen need, this is inorganic nitrogen, of 130 pounds of nitrogen an acre. For no manure, the yield was 66.2 tons for a nitrogen need of 233 pounds of inorganic fertilizer. So the benefits at the MERN over the 3 seasons were 2.3 extra tons of silage and a reduction of the nitrogen needs of 130 pounds an acre, so manure replacing inorganic fertilizer. We are also working on the economic side of this, and Aidan Villanueva worked last year in this What's Cropping Up article where, okay, we know that we are getting extra yield, we are replacing fertilizer, so what's the dollar value of that? He did it for a couple of farms that had 2 years of data, and he concluded that the economic gains in farm 1 were up to $159 an acre, and for farm B, $206 an acre. So putting a dollar value to the extra yield and the nitrogen that you are replacing with manure. So far, what we've seen, the results are site-specific. The response to manure and nitrogen is going to change depending on the history of the field. For our trials on yield 1, in 11 of those, we've seen that there's a nitrogen response and a yield bump. So manure is replacing fertilizer and is increasing yield to levels not achievable with inorganic fertilizer only. In 3 of our trials, we saw no nitrogen or manure response. These are high-yielding fields that have longer manure histories. We also saw large yield bumps and higher nitrogen hydrate needs in those trials where we were also providing potassium that was unlocking extra yield that came with extra nitrogen needs. And for our carryover studies, we have tested year 2 and 3. And in 6 of those trials, we saw a nitrogen response and or a yield bump on year 2 or 3 after the manure application. So the benefits are not only on year 1, also year 2 and year 3. And a couple didn't have response on year 3. So with that, we're going to move from our value manure project field evaluations to our lab evaluations. And these are manure and soil incubation studies. We are doing them in our lab, and what we do is that we collect multiple manures that are present in New York State, and we apply them to these containers with soil at a fixed nitrogen rate. So we apply the same amount of nitrogen in different manures, and then we track mineralization over time. We are conducting them right now during 72 days, and we track inorganic nitrogen. So that's the graph on the right. We see the amount of nitrates in the soil over time, and we can look at the differences in the manures that we are testing. Here is quite obvious. The one on blue, separated digestate, have levels that are way higher to the one on red, digestate separated solids. So this is a quicker, cheaper, and effective way to also look at the nitrogen potential of manure. And we have conducted 2 of these incubation studies, and we have 2 that are currently undergoing, led by Gravin Fernandez and Jamael Chan in our team. So what type of manure are we testing? Incubation study 1 and 2 focus on dairy manures. We were testing for all 4 of them. We have a liquid dairy manure control. This is untreated manure. So we can compare that one, the speed of that mineralization against other sources. So in incubation 1, we were doing digestate, separated digestate, a couple of solid forms of raw manure and digestate. And then in the incubation 2, we had liquid raw manure from a different farm, separated raw manure, flocculated solids, and evaporative solids. These are novel manure treatment technologies. Incubation 3, we have 4 different types of poultry manure that we are working with farms in New York as well, so they're relevant for the state. And in incubation study 4, we are actually collaborating with Jason Oliver and Joel Tinoco in ProDairy, and they are testing some treatments to decrease greenhouse gas emissions during manure storage. So we apply that to the manure, and then we do the incubation studies to see if that previous treatment has an impact in nitrogen mineralization after it is applied to the soil. So it's manure treated with sulfuric acid, gypsum, a biological, and a biological plus gypsum.
So in all these studies, we're looking at the nutrient content and the nutrient release, particularly nitrogen release from these sources. We also want to look into the soil and its microbiology. And we're measuring through the PhD program of the Preet Kaur a whole bunch of soil microbial indicators. Includes working with this microbiometer test kit to get assessments of microbial biomass. And that's been taken along in several of these sites that we had the field trials for. One thing that is important is that manure history seems to be reflected in microbial biomass. And that is something we really want to understand a little bit better and document better. So Capreet is working on our papers trying to document this with the manure sites in terms of microbiology as well. And we hope to have some information for you all in another webinar later in the series as well. Our crediting system, and I explained this earlier in the webinar, it's withstood the time for quite some time, several decades. But with all the analysis that we're doing now, our hope is that we can reevaluate the crediting and tweak it to be more representative of manure sources, and to also recognize the yield bump component that we did not have in the earlier system. So our expectation is that we would have updates in our crediting system for the 2027 growing season and moving forward. Mentioned at the beginning, manure has all 17 essential nutrients. Most of the nutrients, when we calculate with their fertilizer equivalency, when we try to assess how much they bring onto our fields, are calculated equally, with the exception of nitrogen that had a crediting system associated with it, so discounts depending on whether we can capture that inorganic nitrogen. The other one that we need to recognize here, and that's important for agriculture in our region as well, is sulfur. Sulfur deficiencies are not uncommon anymore, and manure does contain sulfur. So I just wanted to create some awareness of the sulfur fact sheet that we have in our fact sheet series, fact sheet 120, where you can get some more information on crediting sulfur as part of your manure application program. With that, we are going to briefly describe a few more ongoing projects before we wrap it up.
So now we have the Power of Manure project, where we are trying to understand what's the soil nitrogen supply and yield potential of ground that has been gone through different agronomic management. We can do it in two ways. Option one is having these no-side dress stamps, where usually we do 3 or 4 of them per field. And the information that we are able to get from these stamps is here. This is preliminary results of nitrogen uptake in manure plots on the y-axis and in no manure plots on the x-axis. So both of them, for each point, they were on the same field, so we can compare the N supply with no side dress with manure versus no manure. So something to highlight here is the 100 pounds mark, that box there. Our current book values are below 100, and we see that very few points are in that 100 mark. Most of them are in the 100 to 300 pounds of nitrogen per acre. So we see that the soil is actually giving us more nitrogen than we expected and that we recognize right now. And also all the points that are left to the dashed line means that manure was actually providing more nitrogen to the soil compared to the no manure stamps. So those are the two learning things that we can see so far with that data. The option 2 for the power of manure is our single strip evaluation approach, SIA. For this, we need a yield monitor and we need 3 previous years of data in order to create this yield stability zone, which tell us which parts of the field are high yielding, low yielding, which ones are variable. So in this example, in the middle, we have a treatment strip where manure was applied the year before. So we were testing the carryover benefit of that manure into year 2. And we just use the place 2 strips next to it, which are the control where no manure were applied, to compare that. Most of this field, as you can see, is red or yellow. So it's zones 3 and 4 low yielding ones. So moving into the results, this is our results table, and because we didn't have zones 1 and 2, that one is empty. But for 3 and 4, we can see in the dark purple that manure application of the previous year increased yields in at least half a ton to 3/4 of a ton. So the conclusion is that manure increased yields in both zones 1 year after application, so carryover benefits. So this is the second way we are doing the power of manure trials.
We have been working on this for 4 years now in terms of value/power of manure, and formed a partnership also with our Chesapeake Bay state colleagues. So Amy Shower, Jared Miller, Roy McGuire, and Nicole Fiorellino from Maryland, Virginia, and Delaware states are joining with a project that they developed to implement similar types of value of manure trials in their states, bringing in results for additional sources of manure, including the focus on poultry manure. So really happy that we can expand beyond New York with this partnership in place as well. With that, we've reached the wrap up. Just a quick summary. Manure contains all 17 essential nutrients. The method and timing of application will determine the nitrogen value of manure. We do want to sample manure as closely to application as possible, so we get a good records of what we actually applied. Ideally, take 3 samples over a spreading event and analyze them separately. Manure can offset fertilizer needs and boost corn yields. We've seen that in numerous of our sites. We also have seen that those benefits carry over definitely into the second year and oftentimes also in the third year. And that database will be expanding with trials this year as well. We see field-to-field differences in crop response and yield response. The field history will play an important part in evaluating the yield-enhancing effects of manure application. That's the research that we're currently working on. Our on-farm research network is really helpful bringing all of this together. So I want to say thanks to everybody that has participated in getting these databases together with field trials and as well as the laboratory work. And we're open to having more people join these type of projects, especially the power of manure stamp plots now in the single strip trials. So if you're interested in joining us, feel free to connect up with us. We can explore ways of doing that. I want to acknowledge all our funding agencies, our participating partners in terms of the farmers, the team members. We presented results that came from different types of projects, all pooled together in a statewide database. I want to recognize all of our partners listed here on the right in terms of contributions to getting this type of information documented. A quick reminder for the webinar on May 1st, it will be about pH and line management.